So Gustav Spies is a company that is producing meat products, and the case study is structured as follows. I give you an introduction, then a motivation, go into process, energy consumption, and temperature data, and give a status of the case studies and also challenges at the end. So Gustav Spies is a family-owned company in Bern-Eck in the canton St. Gallen in Switzerland. It employs 160 persons, and the products are meat and meat products like sausages, ham, bacon. As a Swiss, you know many of these products probably from the supermarkets. So in 2023, they built a new production site here and start producing the meat products in this new buildings and production site. And so this also included a reconsideration of the energy supply, because they have a lot of cooling needs and also heating needs, steam needs to produce this meat. So there is waste heat available from ammonia chillers from the refrigeration plants, and there is also waste heat from air compressors available. And Gustav Spies has CO2 reduction targets. They have the internal goals, but they have also the agreement with the Swiss Federal Office of Energy about the CO2 reduction. And they committed to the Science-Based Targets Initiative to reduce the scope 1 and 2 greenhouse gas emissions by 50% by 2030 on a base of 2019. And also they measure and reduce scope 3 emissions. So the temperatures and consumption and process, so they have this cooking meat process. They have such cabinets where they cook the meats, the sausages at the 85 to 90 degree, and they use steam, low pressure steam for direct heating the meat. And they also have a second network with 8 bar for the heat exchangers to produce dry heat. Today they have a gas boiler, 1 gigawatt hours per year roughly, the energy demand, and in the future they could consider a heat pump, an electrical driven heat pump, covering a share of this heat demand. That was an estimate at the early beginning. So go more into detail. Now this is a schematic how it looks like. So they have a gas boiler and 2 pressure networks. One is a 6 to 8 bar steam pressure network with a pressure reduction. It goes into pasteurization processes. And then for a low pressure steam, they go into the cooking and smoking cabinets. They have in total now 5 or 7 units that are run then continuously with different meats. And the idea would be to include a high temperature heat pump here using the waste heat from the ammonia chillers of 40 to 50 degrees for use 115 or so low pressure steam. So a temperature lift which is somehow suitable in a range that could achieve a certain COP. The capacity of the heat pump around 550 kilowatts. So this was the status 2023. Here you see a picture of the installation of the gas boiler, and then the steam storage, and then the steam network, and here somehow space for a possible high temperature heat pump. You see that the space is quite restricted, so they considered flammable refrigerants not as a a possible solution at first sight for sure, because it would increase the costs for safety installations. So we looked at the possible heat pump suppliers. Here you see 4 examples from Heaton, Oxner, Combitherm and SPH. And these have synthetic refrigerants for that heat pumps. They all provide 115 degree and could produce somehow then steam at that temperature. Here you see also about the rough cost estimations and the COPs for these temperature conditions. From SPH, we could also get an offer for butan for a hydrocarbon solution. And so in average, so the specific investment costs for this equipment would be between 840 to 1,000 euros per kilowatt for the HFO refrigerant solutions and 1,300 euros per kilowatt for the butan heat pump. The COPs between 2.4 to 2.9. So this was the status early this year. So with that information, we can do a rough cost calculation. So we know the temperatures. So on the heat sink and on the source side, a temperature lift of 65. In that case, we assumed a heating capacity of the heat pump 550 kilowatt. We had some information on the gas price and electricity price. So the electricity price quite high, but also the gas price was quite high at that point. So today this gas price is much lower again. So this would make the case more difficult. Then also CO2 tax here, a CO2 emission factor for the electricity, which was assumed quite low, like renewable electricity. They have PV on the roof and also have a good contract for the electricity. Then the gas has this emission factor, and the operating time was assumed to be 3,000 hours per year. Efficiency of the boiler 90%, maintenance factor 4% on the capital cost, and a cost factor for planning and integration a factor of 2. With the temperature lift of 65 Kelvin, a COP of 2.67. So it's a good fit curve actually that would fit also the heat pump supplier offers, the COPs from there. And this would give then investment cost specific of 840 euros per kilowatt. We used this as a starting point. Then as output parameters, total investment would be then 924 kilo euros and could reduce CO2 emissions by 98%. So it's almost a complete substitution. Energy savings also 66%, so substantial. Cost savings for fuel, electricity costs, these are additional then the heat pump maintenance costs and CO2 tax. So totally annual cost savings 153,000 euros with a discount rate, or then this gives a static payback time of 6 years with a discount rate of 5%, 7.3 years payback. So this was a first estimate based on some knowledge in the early stage of this project. We also did then a sensitivity analysis, and this is always required to check the different influences of the different parameters on the payback time. And here you see such a possible visualization of the payback period as a function of these different parameters. And you see the electricity price has major influence on the payback. So the electricity price and also the fuel price, they give somehow the upper boundaries. So then, okay, the investment costs, the temperature lift has influence with the COP, and so on. So from that, we did additional sensitivity analysis changing only one parameter here. Here it is the electricity price. You see here the broader these areas, or the more how do you say sensitive it is on the payback. The temperature lift also important. So if we increase it, then the COP goes down and the payback time goes up. If you have a higher cost factor for planning integration, then also the payback go up. So this is a possible visualization for this case. So we can draw some preliminary conclusions. This was also published or presented in a poster at the High Temperature Heat Pump Symposium in Copenhagen. So yeah, the payback period is influenced by the electricity and fuel price, by the temperature lift, by the investment cost, by the operating hours, and the cost multiplication factor for planning and integration. Waste heat from ammonia chillers as a heat source is available, and in principle, this is often the case in food companies where they have chillers, electrical driven refrigeration chillers, and a gas boiler, so fossil fueled system for producing steam or hot water. So it has a lot of multiplication potential. But we also recognize there is a need for technical support for the integration, because this is not available at the company. So at this, let's say, company with 160 employees, there is 1 or 2 persons that would deal with such energy questions and possible integration for a new heat pump. So they need external support. So the next step was then to have real data, so monitoring data and pinch analysis. And this why now, because this is a case where the production just started with this new building, with this new production site, and the gas boiler was installed and running, and so the first months of this gas boiler could be monitored to see really the steam demand. So the pinch analysis was quite simplified or simple in this case. Here is an example. So they have a steam demand, 110 or so degrees, and a waste heat available from the chillers at 40 degrees. So this gives about a pinch temperature of 70 degrees. In this case, not all streams were, let's say, included. It is a more average representation of a 11 hours time slice. But you can see that the steam demand is here 125 kilowatt. So this gives confirmation that the temperature levels that were estimated at the beginning can be used for the heat pump. It's quite challenging to reach this temperature lift, and the COP is rather low, so 2.5, somewhere in that range. Then the steam profile was really measured with a sensor, and you see there is a lot of fluctuation. This is a daily profile over 24 hours, and yeah, it's very fluctuating, so it's not steady. So this means there must be some storage solutions as well. And we also recognized that the 550 kilowatt estimate at the beginning is rather high. So to cover the base load, a smaller heat pump of maybe 300 or 350 kilowatt heating capacity would be enough, and then covering the peaks with a steam storage. And this is also shown here with the cumulative steam demand, so the kilowatt steam over the operating time, and you see that 300 or so kilowatts is only needed a few hours. So let's say 200 hours, 300 or so kilowatts. So this whole further analysis and monitoring of the real steam profile is very, very important to make really decisions. And so we can conclude at that status of the project that, okay, a steam generating heat pump is technically feasible, but we have economic challenges. Quite high temperature lift, low COP, high investment costs compared to other technologies, let's say. And now we also recognize quite low operating costs, operating hours, and very much fluctuation of the steam demand for these sausage and meat cooking cabinets. And the electricity prices are higher now again, and the gas prices are lower again. So all of these four parameters are not so much in favor for the heat pump. So it's really a message here. We need to always to have the real data, the steam profile and monitoring data to make decisions, because these are the parameters for sizing the heat pump to define the heating capacity and also the storage vessel volume. And this pinch analysis is a support method for decision making, and it's really needed to have a better view and to the energy situation at the site. So we know then the pinch temperature and the heat recovery potential, the hot utility demand, and the cold utility demand for that site. So we have published about Gustav Spies and the meat case studies, a poster and some papers in some conferences. Here are the links. And yeah, so that is the case from Gustav Spies. Thank you for your attention.